My name is Onur Apul. I'm an assistant professor of environmental engineering at Maine. Relatively new on campus and moved here in September 2020. Today I'm going to talk about one of my students' recent review study, thermal regeneration of spent granular activated carbons to break the forever PFAS cycle. Her name is Busra Sonmez, and she was a grad student with me at UMass Lowell. Now she actually got accepted to the PhD program at UT Austin. She's moving to Austin, Texas soon. This is a multi-institutional collaboration. We have Yi Zhang. She's a postdoctoral research associate at Stony Brook University. We have an assistant professor of chemistry, Dr. James Ruther from UMass Lowell, associate professor of environmental engineering, Dr. Navid from UT Austin. And we have Dr. Arjun. He's the associate director of New York State Center for Clean Water Technologies. First, if you have any questions about this talk or any other correspondence, you can email me from onur.apul@maine.edu, or you can check out my website. I try to keep it up to date about our recent publications, news, and job ads, and so on and so forth. I know we have seen PFAS molecular structure a lot, and I know a lot of you is familiar with PFAS. But PFAS stands for per and poly-fluoroalkyl substances. It's a mouthful. It's a synthetic compound. It's an umbrella name for thousands of chemicals. The most popular ones or infamous ones are PFOA, PFOS. Their structure is pretty unique. There is a long chain of carbon saturated with fluoride, specifically if all these carbons are particularly saturated with fluoride, we call this structure a per-fluoroalkyl substance. If some of these carbons are not saturated with fluoride, then we call it a poly-fluoroalkyl substance. So the general name becomes this mouthful, per and poly-fluoroalkyl. They have different chain lengths, they have different branching and different functional groups. The carboxylic acid functional group. There is the number of carbons, give this unique name of PFOA, perfluorooctanoic acid. Not only the hydrophobic tail and hydrophilic functional group, this is also unique in terms of strong carbon fluoride bond. Carbon fluoride bond is the strongest covalent bond that carbon can form. It takes 544 kilocalories to break 1 mole of carbon fluoride. It's much stronger than carbon-carbon bond, so defluorination of this molecule is quite problematic. Also, typical approaches would use radicals or superoxides to break down and oxidize organic chemicals, in addition to environmental light or bioremediation processes. But fluoride basically is such an electronegative atom. It pulls the electrons from carbon and it forms a partially negatively charged shield around this whole molecule. So this whole molecule is shielded by a partial negative charge so that hydroxyl radicals cannot really approach, or even microbes do not really like to use this electron donor. So this molecule, that's why it's very sturdy, very stable, makes it very desirable to use in household domestic products because it's resistant to heat degradation. It's stain and water repellent. Diane was talking about oil repellent abilities, just like a surfactant, looks like a surfactant. It repels oil and water. Same time, we coat food packages like microwave, popcorn bags, food wraps. With this, I'm not endorsing or any product. I'm not releasing any fear-monger, hopefully, because I don't know the current state of any of these products. These are just examples. There are current efforts to regulate these products and take PFAS out of the market, but just letting you know why this is such a problematic chemical because of its desirable attributes that we use in daily life. So this hydrophobic tail and hydrophilic water-liking, water-hating structure also makes it a good fire suppressant. It forms a thin film on water. Therefore, it basically suppresses the penetration of oxygen and kills fires. Being used heavily in industry, domestic products. Of course, once something is used heavily in industry, in commerce, and we start seeing it in the environment. So this extensive use yields a global environmental abundance. It's not a local problem. This is a global crisis in both natural environment, natural aquatic environment, and engineered aquatic systems like water treatment plants, wastewater treatment plants. So the situation is not different in Maine. Maine DEP releases up-to-date data on their website. This is a snapshot from the website. You can actually click on these yellow dots and read it. Some of these dots contain up to 1,000 data points. You can read the measurements, recent measurements of PFAS in these soils and waters, wastewaters. The data is getting updated. In 2020, early 2020, when the pandemic was first hitting, Maine DEP task force released a report explaining that there are 30,000 records for 28 different PFAS at 245 locations. 1 year, maybe a short time frame for research, but it's a really a long time frame for PFAS research. So considering this long 1 year difference, I'm sure the numbers have exponentially increased. This is a very dynamic area, so there's a lot more data out there. More recently, including our acting commissioner, Melanie Lloydson, and other New England environmental protection leadership wrote a letter to EPA incoming administration and urging the importance of PFAS issues to protect our environment and citizens. So this local situation, this is a simplistic model that Busra generated. This is basically showing that forever cycle of PFAS in the aquatic environment. On the left-hand side, we see the point sources like manufacturing, industrial use, large-scale use, or non-point sources like firefighting foams we saw earlier this afternoon, or the general population is using this, and eventually they may end up in landfills, in wastewater treatment plants, and even in the atmosphere. Atmospheric transport can take them towards even isolated regions where there is no PFAS production or uses, but wet and dry deposition can end up transporting these chemicals to where we least expect them. Surface runoff, groundwater percolation may pollute surface waters, groundwater, and if downstream, if they are used as a drinking water source, either by a public water utility or by private wells, they will be containing PFAS. So this cyclic motion, same thing, we can follow a solid waste path. We have landfills, incinerators. I'm not saying these are sources. These are very important environmental control measures, and they help us stop, contain PFAS, and maybe even destroy them in incinerators. But if not understood properly, they may be another source of secondary PFAS pollution back into the environment. Same thing for wastewater treatment plant biosolids. Same thing with landfill leachate, landfill runoff, uncontrolled runoff, or land application of solids. So this creates a cyclic motion of PFAS, and I'm going to focus on one particular area, the use of granular activated carbon. Since we have an emerging crisis of PFAS in drinking water sources, I was also very surprised to hear that foamy water coming from citizens' taps, showing that there's an urgent crisis. And although there may be several research attempts to destroy PFAS, non-destructive removal, meaning adsorption, ion exchange, filtration, still posing a gold standard for PFAS removal. So once we say your source is PFAS, we also have to say that we are doing something about it to the consumers. So currently, granular activated carbon adsorption is one of the gold standards. So there is going to be a nationwide surge of applying PFAS removal systems with GAC, granular activated carbon. and this surge is going to create a new line of waste, PFAS-laden GAC. So there's going to be a lot of solid waste that contains PFAS, and what we are suggesting is that GAC regeneration, which is an industrial process. So once the GAC lifetime is over, typically you send it to a regeneration facility if it's economically feasible. But these are industrial scale operations where you heat up the GAC, get rid of the organic content, and also reactivate the carbon. And instead of throwing this away, you create a regenerated carbon that has hopefully a similar adsorption capacity. So what we are suggesting that this regeneration step could be a key step, considering the surge in the amount of spent GAC with PFAS on it, could be a key step to break this forever cycle if we can destroy PFAS at this step. I see messages. The objective and scope of this work was a critical review of 110 recent publications to understand PFAS-loaded GAC regeneration. Our scope, basically our study starts with a spent GAC. So we have GAC particles loaded with PFAS and probably other co-contaminants. And then we have a process of regeneration where we apply heat in different ambient gases, different heating ranges, heating ramp, and final temperatures. And then hopefully we have this carbon structure maintained. This is a very fragile carbon structure that's combustible, but PFAS is gone. The PFAS is hopefully destroyed, not into a shorter chain PFAS or more problematic organofluorides, but it is mineralized. This is, of course, ideal. And then GAC has no changes in its structure. I describe this as scratching the back of a mosquito without killing the mosquito. It's such a diligent process to make sure that we recover GAC and we destroy PFAS at the same time. So in our study, we investigated the role of PFAS properties, investigated the role of this regeneration step, and also the controlling parameters in GAC properties to discuss the regeneration success. Okay, first, I'm going to show data for, again, these are literature data for comparing different carbon chain length PFAS from 4 to 8. And we are looking at percent decomposition, meaning that PFAS is gone from the surface of the carbon. If we just focus on one, maybe the orange one, you can see as we increase the temperature, we are removing more and more carbon from the surface of the, more PFAS from the surface of the carbon. The lower temperatures, we only have about 70% removal, but we can go all the way up to 100% if we go around 775 degrees Celsius. If we go from long chain to shorter chain PFAS, overall, our success of decomposition is getting worse and worse. For short, better and better. For short chain like C4, we even at 175 degrees Celsius, we have 90 to 100% removal at every temperature. So we think this is something to do with the volatilization of carbon, because the boiling points of these 4 to 8 chain PFAS molecules show also an increasing trend with carbon chain length. So the more stable at higher temperatures the molecule, the more likely, the less likely to remove it from carbon surface. So we think we are observing here is may not necessarily be decomposition, maybe just removing it from carbon surface. And we look at the same thing, but in terms of thermal destruction this time, the temperature suddenly got much, much higher. Instead of 100, 200 degrees Celsius, our lowest temperature reported is 700 degrees Celsius. And thermal destruction, meaning that removing a fluoride from the structure, so defluorination. So we have data for PFHXA and PFOA. We don't really see a substantial difference between the two of them, but we know we can achieve 50% to 80% removal with this temperature range of defluorination of these compounds. So we are basically mineralizing or destroying them to an extent. Here's a different way of looking at the same data. when we compare 4 and 8 carbon PFAS with different functional groups, carboxylic and sulfonic acid functional groups for 8 carbon and 4 carbon, which is the logic here was 8 carbon was the original PFAS that was seen, shorter chain was an alternative, and then GenX was another alternative. So we are seeing a very similar pattern of carboxylic acid ones, PFOAs, seem to be very easy to recover. So we get 75% recovery at 175 degrees Celsius. So the white ones means it's recovered, black means it's retained on the carbon. But sulfonic acids, PFOS in this case, is retaining on carbon surface. And when we place the boiling point of these compounds on this chart, so we can see there's actually a rough relationship between the boiling point and removal of these PFAS from carbon surface. Same thing for 4 carbon alternatives, but GenX was thermally least stable because its boiling point was the lowest between all of these. Of course, we value the destruction of these chemicals into shorter chain, ideally into minerals that are not concerning for us anymore. So we think what's happening is at higher temperatures above 700 degrees Celsius, we are producing 2 major byproducts. These are not experimentally confirmed because finding these transformation byproducts standards even are not very easy. But what we are thinking that's happening is defluorination of removal of hydrogen fluoride and carbon dioxide if we have a carboxylic acid group here. Or similarly, we have HF and SO3 removal if we have sulfonic groups. And we also have an alternative pathway that shows that HF and carbon monoxide and HF and SO2 are removed from the chains at 700 degrees Celsius or more. But the more interesting thing was defluorination rates. Sorry?
5 minutes.
Thank you. So the more interesting thing was the defluorination rate of these chemicals, PFOA. So these percentages you see are defluorination of analytes. So there is no carbon in these percentages. PFOA and PFOS, for example, 30 and 48% defluorinated at 700 degrees Celsius. But when we put these same compounds onto carbon and then go to the same temperature, our defluorination increased by 70%, by 60%, by 44%. So somehow, when PFAS was on carbon, its destruction was catalyzed. So we think maybe this is either a physical restriction of PFAS molecules on this carbon. So we are constantly flowing through an inert gas like nitrogen gas in this regeneration chamber. So maybe this carbon gets really hot, but cold gas is flowing through, and carbon helps trap these molecules, trap and release within the pores. So it increases its retention on this hot surface. So it doesn't get destroyed, it gets destroyed better. Or maybe the electrons of the carbon surface may have an electronic interaction and basically catalyzing the reaction in a favorable way to destroy PFAS if it's on carbon surface. We don't have further information about this, and literature is very limited about why PFAS is destroyed better when it's on carbon surface. One aspect is what happens to PFAS. We want to make sure it's destroyed and becomes harmless. The other component of this is the carbon. So these are commercially available granular activated carbons. We look at their surface area before and after regeneration. At different temperatures, color-coded, at different temperatures, GACs are losing 100% of the time when we regenerate them. So there is always a loss. It's not ideal. We would like to have the original carbon and the regenerated carbon to be almost identical, but almost every carbon we are seeing a decrease, about 55% decrease at low temperatures and 22% decrease at high temperatures. We think at high temperatures, we are removing some char and byproducts that are plugging the pores can also be removed at high temperatures. One interesting observation was every carbon that you have seen in this list that is tested for PFAS removal was a coal-based carbon. All of them are made by coal, but the product raw material of these carbons, such as wood or coconut shell, would make an impact on their morphological properties and also their durability under heat. It may be worthwhile to looking into different, more mesoporous, more macroporous carbons made from different raw materials. But currently, we only have data with coal-based carbon. Another carbon property that is important for adsorption of PFAS is pore volume. This is the data that you saw in the colorful chart. BET surface area, and again, in 100% of the case, always goes down all the way at 80% carbon surface area loss to 4%. So we have a wide range of surface area loss, but it's inevitable. We always lose carbon surface area. So pore volume, same thing. Mesopore volume, not always. Sometimes it increases, sometimes it decreases. But another important metric is micropore volume. Micropores are the primary sites. PFAS are very small molecules, and they would prefer to tuck themselves in smaller pores with multiple attachment points so they can decrease their internal energies. So micropores are very essential. So again, 100% of all the studies, micropore volume was decreasing. One way to recover this, the studies tested regeneration and reactivation, which is a subsequent step using a strong oxidant, steam, or a hot carbon dioxide to recover and reactivate the carbon pores. So this is an important step to make sure that we apply. So the general conclusions from our review was the thermal destabilization or decomposition of perfluorinated carboxylic acids were in general more favorable because their boiling points were lower and they were destabilized from the surface and they were in the gas phase rapidly. Longer chain ones versus shorter chain PFAS were harder to remove because they are hydrophobic. They have better interactions, better non-specific interactions with the carbon surface. So long chain ones stick on the surface harder, and it's harder to remove compared to short chain. At low temperature, we think what's happening is volatilization. PFAS basically goes into gas phase. It's a gas phase transport. At high temperature, we can achieve thermolysis, not as much as 90, 100% like volatilization, but we can do 50, 80% at temperatures at 700, 1000 degrees Celsius. But thermal transformation is happening when there is carbon more rapidly. So when the carbon actually catalyzes the thermal transformation of PFAS into something else. Of course, our knowledge is very limited at this stage, but we know the carbon surface area goes down, pore volume goes down, micropore volume goes down, but high temperature reactivation, strong oxidants can recover the surface area. So if I could have one take-home message, I would say it's possible to destroy PFAS, and actually it's more favorable when there is GAC, when they are on GAC surface. And GAC surface thermal regeneration may not be retained during the regeneration step, but we can reactivate and maintain majority of the physicochemical properties of GAC. That will be a two-bird, one-stone situation. While we recover the GACs, we also break the forever cycle of PFAS. Currently, we are setting up an experimental evaluation to see what's the effect of PFAS, changing properties of GACs, and also understanding the proposed thermolysis pathways are correct or not. And also we are looking at different GAC characteristics. How do they change? Are they preserved? And are those changes favorable or not? And this, of course, the physicochemical integrity of different raw products for GAC is going to be evaluated. So this was funded by USGS last year as a 104B program at UMass, and the slides, and of course, were prepared by Busra, and of course, she was leading the this effort. This paper is currently in review, except with minor revisions in environmental science and technology, and I would like to thank you for your attention. If you have any questions, I think we are going to have a Q&A session at the end of the